Let's make a list of the topics we want to cover. You don't need to know mechanisms for epoxides or alcohols, but we can look at mechanisms if it helps you understand why they do what they do. So I'm happy to look at that if you want to. I was thinking you guys might want to see EAS and NAS mechanisms again. Should I put that on the list right away?
Yeah.
Oh.
Yes.
Okay.
Sorry. Sorry, I didn't mean it. Yeah.
Because I feel like when we did them in class, I didn't give you guys a lot of examples of how to get to the major resonance forms and between major resonance forms. So I kind of want to demonstrate what that should look like. I will say, when I put these mechanisms on your homework, I was not aware of how many arrows it could take to get to just the major resonance form. So on your exam, I was mindful of how the resonance form of the aromatic ring is placed to get to the major resonance form more quickly, to give you a little bit less work. So I'll demonstrate what that means. What else?
Actually, I was going to ask if you could go over, like, thinking the major resonance form again.
Major resonance forms, yeah. Definitely. Broad topics, specific questions. What do you got?
I was going over like the practice exam, and I noticed like some of the reactions are referred to by like the name of the reaction versus like
The reagents.
Yes.
Yeah.
Yeah. Maybe we could go over some names again.
Sure. I will say I do my best to give a systematic name and not dead people's names, or both, right? So but it is good to know what the reactions are called. That's an important conceptual connection. You're not just memorizing reagents. You're understanding why those reagents do what they do. Yeah, we can talk about them.
Yeah, I think there was only like 3 questions like that, and 2 of them were like pretty intuitive, but one of them I was like, association and
Sure, sure.
I was like, I don't know.
We'll go over it. What else?
Epoxide?
In general?
Yeah.
Okay. We can try. How about, okay.
Yeah.
Clocked it? She's like, what are you pinching at? Oh, God. They're going to revoke my gay card.
Never mind.
Nothing. Just forget I said that. Edit that out of the video. What else? Say that closer to the mic, please. Is that an inside joke I missed?
What?
Oregano metallics?
I couldn't pronounce it, and I kept pronouncing oregano. Now it's just oregano.
Anything in specific about oregano metallics?
I feel like you went over it like really quickly, and I missed some stuff.
Okay.
I just kind of wanted to go over it again.
Mm-hmm. Yep. Okay. Indigo?
Like attaching a carbon group onto the end of the carbon chain.
Yes.
Okay.
Yeah, I like that.
Carbon-carbon bond formation to elongate a chain.
Yeah, like they'll have like a alkane and then ask you
Do you have a problem in specific that you're thinking of, like from active? Because you said those always.
I didn't write it down. I couldn't tell you what homework it's from at this point.
Well, probably from the alcohols, where the okay, maybe we can find it, but starting with alkane and attaching a longer chain. Katie, you had something.
There was one, I feel like, on one of the written ones recently. There's like a methyl brown. Let me see if I can find it.
Okay, I don't know how to write it down, so I'm gonna try to say.
I remember like the first one on the alcohols and epoxides homework has a methyl group with the alcohol group next to it. And I was having a hard time trying to figure out how to add the.
Do you have it up?
Yeah, I have it right here. Like adding this methyl group with the alcohol at that spot.
Okay.
At the same spot.
Sure. And you know it's not in one step.
Yes.
Yeah.
Yeah.
Can I show this to her?
Yeah.
Indigo, is this what you mean? Something like this? On the left?
No, it's like, it gives you like the whole chain thing and then asks you to like attach it. Because it had like a alkane chain and then
Yeah.
it asks you to attach like a piece like this, but attach them here. And I don't, wouldn't it prioritize that one?
Yeah, I feel like I want to find a problem. Do you have you don't have a way to get your homework here, do you? Maybe we can scroll through some of them.
Yeah, and you can just put whatever you want on there.
PCl3. Where do you have it?
The alcohol, number 12. So this one, yeah, kind of like trying out. This is the only choice on this one, and it says.
Oh no, really?
Yeah.
Oh.
So this one, what it is.
Shoot, I forgot. I ought to just remove that whole thing then, because that is not a reagent I use. So there was a homework problem you had on active that had you take an alcohol to an alkene, which I think most of you would use sulfuric acid catalyzed dehydration. But the only answer that worked was POCl3, which is not a dehydrating reagent that I use in my classes. It's hard. Actually, I was thinking about this last week when we did alcohols. You guys were also doing oxidation of alcohol in lab. You took benzoin and you oxidized the alcohol into a ketone and made benzyl. With nitric acid?
Yeah, it fell into the water bath. We got 50-50.
Yeah.
Wow.
That was a thing that happened.
Oh, it's okay. I threw my whole product away today.
Oh. So
We did that too.
your oxidizing agent in that lab was nitric acid. But did you notice me give you nitric acid as an oxidizing reagent in class? Chromic acid, PCC, MnO2. So why are we using an oxidizing agent in lab that we're not using in class? It's because chromic acid and PCC both have chromium, which are heavy metals and are not great on the environment to use. Nitric acid does the same thing sometimes with secondary alcohols, is easier to use, less harmful on the environment, no heavy metals.
So is it more of like a mild oxidizer than a strong?
I actually don't know how nitric acid reacts with primary alcohols because I haven't seen it, and textbooks don't usually report it. So in lab, you used an oxidizer that we don't really talk about in class because it's just easier to use but not as common in a hardcore synthesis teaching environment. Okay, you won't have to know that one other than on the homework. And you said that was question 12 on the alcohols, section 16, question 12. I'll just give that to you guys. That was not meant to be a challenge. Sorry.
Why is the online
I don't know what you mean. Because it gives you that hexagonal framework, right? And then what does it tell you is wrong about it? Are your carbon chains wrong? I find what it yells at you the most about is not putting lone pairs.
For the skeletal, I thought it was just assumed if we didn't have to put a lone pair.
Is that what you mean? That's what it yells at you about?
Yeah, it's like yelling at.
Correct. I agree with that assumption. So you don't have to put lone pairs on my exams. But active often looks for it without explicitly saying it. And sometimes they don't look for it. My OCHEM 1 class, it gave them this molecule and it said, you guys might have had this too. Predict the major daughter ions that form from alpha cleavage. This is how it gave it to them. Notice how many lone pairs are shown? None. It assumes, like we do. And then my students would put in the major daughter ions, wrong, 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 and the feedback is never, you're missing lone pairs. The feedback is something in your structure is missing. Great. So why are they not accepting answers for an assumption that they gave at the start? I know, that is the worst part, but in my opinion, it is the lesser of two evils against a lot of the other homework systems. A lot of the other ones are not as straightforward. Active was designed by chemists for chemists, and I see that, which is why I stay with it. Yeah.
If I'm getting it wrong, I can just be like, try the lone pairs, and if I still get it wrong, just bring it to me.
Yes. First try the lone pairs, then bring it to me. Okay.
Still that question, they have another agent called Martin for iodine or something.
So yeah, Des Martin does the same, and I think they might even list it as DM. Maybe you can send me an email and ask me to remove that question from my homework so that I stop having it. Because there's two reagents that I don't use, and that's not something I want to have. Des Martin does the same thing as PCC. It's a mild oxidizing agent.
Can you add whatever you want with MGBR?
Yes and no. Whatever you want cannot have a carbonyl and cannot have an acid of any kind, like an OH or an NH.
But you can have like an O minus on there?
Yeah, probably, but I've never seen somebody add a Grignard with an O, like an alkoxide on it. If that's what you're trying to do, there's probably another way to do it. You're talking about the homework?
Yeah, I did, yeah.
Yeah, there was another way to do it, which was instead of having a nucleophile on one carbon and an alkoxide on the other, why don't you just have an epoxide that you attack with a nucleophile?
My brain said no.
Yeah. So that reagent, like, it did work, but it doesn't resemble anything similar to what we've done. And it's not something I would recommend using in the lab. Like, I'm just not quite sure how it would work.
But you can add like alkenes on there?
Yeah.
Oh.
Yep. But your compound cannot have any sort of CO double bond. A CO double bond is too electrophilic, so it would attack that.
Okay.
Acyl addition.
Okay.
Did you want to add something to that? No? I thought I heard something.
No, I already forgot.
That's okay. All right, should we dig in? I think let's come back to the mechanisms because that felt like a hit or miss thing. I think a lot of you felt pretty strongly about organometallics, which tie in pretty well with epoxides. So let's start there. 3 types of organometallics, and to be honest, one of those types will not show up very much on this midterm, if at all. 3 types. Who can name one of them? Oh, yeah. So one is the Grignard. That is organomagnesium halide. One is the organolithium, which does not have its own name. And the last one is the cuprate. No, you don't have to show mechanisms for these. The mechanisms that I will ask you on the midterm, you'll have a choice. There's one EAS mechanism and there's one NAS mechanism. Those are your choices. One mechanism, either EAS or NAS. What do you mean? That was never a question. That was always the expectation. I told you that from the very beginning.
Well, yeah, we've only learned like one mechanism, so it would be weird if you asked for more.
I agree. We did do mechanisms in Unit 1 with the OCHM 1 review, but that wasn't as relevant here. So it was always going to be NAS or EAS, always a selection between the two. Probably always will be for as long as I have the right. Okay, these are our organometallics. James?
So when we use the organic lithium, do we use two portions of it, or is that just for the case of like from
To make the organolithium?
yeah, I guess. Or, yeah.
To make the organolithium requires 2 equivalences of lithium for every equivalence of organohalide. To make the cuprate actually requires half an equivalence of copper 1 iodide for every equivalence of organolithium, or another way to say that is 2 equivalences of organolithium for half an equivalence of copper iodide. Which of these is not like the others? Nope, but good try. Right. The cuprate is not like the organolithium or the organomagnesium halide. But I'm curious why you thought the magnesium one was not like the others.
Because the rest kick off what used to be there and magnesium just
Okay. So the magnesium kind of inserts itself and it doesn't remove the halogen. The lithium does completely get rid of the halogen, and the copper kind of gets rid of the lithium, but it does totally replace where the lithium was on the carbon chain. However, that difference is small in comparison to the difference between main group metals, S block metals, and inner transition metals, D block metals. Copper has d orbitals that it is using to do bonding, and lithium and magnesium are using s orbitals. This can do much more complex things. You might remember I did show you the intermediate that copper can form during its substitution reactions. It can go from coordinated to 2 things to being coordinated with 4 things. And that's how it's able to substitute groups. Magnesium and lithium are not really bonded. I actually still don't quite understand why organic chemists will show these as covalent bonds. I don't appreciate it.
How would you?
I would show it as a carbanion. Since we know that these are basically just spectator ions, they're going to be in the waste. They're not doing anything. I would show this as carbanions. But I won't, because you're not going to see anybody else out there do that. And I already do some wild stuff. So I try to keep it in bounds, you know? Because I'm not preparing you to go work in my lab and think the way that I think. I'm trying to prepare you to take the MCAT or the DAT or whatever entrance exam you need. and have a baseline ability to rationalize what you see. That's what I'm, and a couple of you might do chemistry. And maybe a handful of my students my whole career will do organic chemistry, but this is what most people are going to see. So that's what I show. Okay. Sorry, good review. These are how we make our organometallics. These are essentially equivalent to each other. This one is unique. Here are some of the distinctions. This can run SN2 and acyl addition and SNAR, aka NAS. This can run SN2. I should not have switched colors. I'm using the wrong color to coordinate these things. This can do SN2. It cannot do acyl addition. But it can also do SNAR, and it can do SN alkene. That's not a name I've ever written before. I just made it up. It can substitute halogen groups on any sp2 carbon. Nothing else can do that substitution. And it's because of the d orbitals. These depend on nucleophilic attack to break a bond. But this actually breaks a bond, separates them by bonding them both to copper, and then swaps out what the things were bonded to. It doesn't necessarily do a nucleophilic attack like what we would expect it to be. I know I'm calling it SN2, which implies a nucleophilic attack, but it just resembles that. And since we're not getting into the mechanisms, I don't have a better way to try and, I just want you to see that pattern. Speaking of naming, like Peyton was asking, acyl addition. What does that mean? What is acyl?
I don't even remember acyl addition.
Carbonyl.
That one.
Another way to say it?
Carbon double bonded to an oxygen.
Good, CO double bond. Addition consumes a pi bond. So this addition process will add something to both groups. Unfortunately, there's a lot of acyl addition where we add two things to both groups, but this selectively means nucleophilic attack by like a carbon reagent. So a couple of acyl additions that we've looked at. You should be so proud. What kind of organometallic do I have here? Grignard, good. Why is it written over the arrow? Why isn't the carbonyl written over the arrow? Good try. They can't be in the same molecule, because if they were, they'd react. But why is the Grignard over the arrow instead of before the arrow? Why isn't the carbonyl over the arrow? Artist's choice. Dealer's choice? What's the artist? I don't.
You're the artist.
Oh, thanks. Doesn't matter. It's totally arbitrary whether you show one reagent or the other over the arrow. A lot of times it's like, what do I have and what am I going to add to it? Or what have I made and what do I want to add to it? Why is this not the product? Good. This assumes a hydrogen that is not present in the reagents. And you know what happens when we assume. So we need to add two steps for acyl addition. in order to get that protonated alcohol. Katie, earlier you asked, start with an alkene, and at one position I want to add both an alcohol and a methyl group.
Exactly.
First of all, I would describe that methyl group. What is the substitution of that methyl group? Sorry. Describe that alcohol. What's the substitution of the alcohol? It was a tertiary alcohol. We can make tertiary alcohols by acyl addition to ketones. You guys might remember this little chart I made last week that showed reduction versus acyl addition. Do you guys remember this?
Yes.
What I wanted you to see was, and maybe I'll try to reiterate this again. I wanted you to see the relationships and the connections between all of our different carbonyl groups and alcohol groups. So formaldehyde can be reduced. This is my reducing agent, LAH. Is this a strong reducing agent or a mild reducing agent? Strong. So I could have shown NaBH4 in place of LAH. What am I missing from my reduction step? Aqueous workup. I'm skipping that for now because it gets so cluttered. But any reduction step, I do want to see that aqueous workup with it. If I add an organometallic to formaldehyde, I create a primary alcohol. If I, oops, that was not supposed to be an M, that's an OH. So formaldehyde is a useful precursor to methyl alcohol or primary alcohol, but by two different means. If I oxidize this with a mild oxidizer, I can make an aldehyde. And my aldehyde can be reduced to an alcohol, of course, because reduction and oxidation are just inverses of each other. If I do acyl addition to my aldehyde, what is this substitution? How substituted is this alcohol? Secondary alcohol. If I oxidize my secondary alcohol, yes? Oh, I thought you said wait. If I oxidize my secondary alcohol, I can get a ketone. Of course, reduction of that ketone takes me back to the secondary alcohol. What I'm trying to point out is when you're analyzing these groups, think about their substitution, because that will tell you what changes are possible. I want to make a secondary alcohol. Well, one way I could do that is by acyl addition. Maybe I should consider forming a carbon-carbon bond and making an alcohol at that position. I want to make a secondary alcohol. One way I can do that is by reduction of a ketone. Maybe I should consider having a ketone starting material and reduce it.
Are we assuming that the other red line is also adding PCC?
Thank you, yes. Okay. This other red line is, but with, in the case of the oxidation of the secondary alcohol, it could also be chromic acid. PCC and chromic acid have the same effect to make a ketone.
And also with the RM, are we just like, could we use just magnesium, or does it have to be like with the halide as well, like magnesium bromate, the MgBr? For like the RM on the line.
Yeah, RM could be Grignard, which is organomagnesium bromide, organomagnesium chloride, or it could be organolithium, because these do the same thing. But we should not use a cuprate because it's not a good reagent for acyl addition. It's not actually a true nucleophile. I don't think I've ever put that together until right in front of you right now. Okay, and if I try to oxidize my tertiary alcohol, no reaction. No hydrogen from that carbon can be removed. So I can't replace a carbon-hydrogen bond with a carbon-oxygen bond. Let me ask you this. What would happen if I took any one of my alcohols and I tried to react it with an organometallic? But it's not no reaction. Because last time you told me it straight away, no reaction. But this, you're like, it doesn't work. But a reaction does occur. The organometallic becomes protonated. It gets a hydrogen back. It just becomes an alkane, an alkene, an aromatic ring. And the alcohol becomes an alkoxide. So earlier, somebody asked, can I add a Grignard with anything else on the molecule? Not really. If you form an organometallic on a molecule that has an alcohol, it will find that alcohol and deprotonate it. Now your organometallic is destroyed, right? Imagine that these are linked to each other. They do an intramolecular deprotonation. If I have an organometallic on the same molecule as a Grignard, Grignard, sorry, organometallic on the same molecule as an acyl group.
I was gonna ask if, so like with an organometallic, so is that why you can't do like a MgBrOH? Do they just like destroy each other? Or
Yeah, MgBrROH, like
yeah,
this?
like if you were to do like that, like all combined, would they just like
Yeah, they turn into just whatever your MgBr was. Am I misunderstanding something?
Oh, I was just saying, like, if you, like, react, or, like, when we do, like, MgBrCH3, but instead of CH3, if you did OH, like MgBrOH.
That's just a salt, magnesium bromide hydroxide.
And that doesn't do anything.
Mg2 plus, Br minus, OH minus, that's just an ionic compound.
Okay, yeah, I was just saying, like, you wouldn't add an OH on that way.
Correct. Correct, it does not work like that. Due to the electronegativity difference between oxygen and carbon. The carbon will have a different property than the... This would be a source of hydroxide, but it typically precipitates. Hydroxides are generally insoluble. I do want to point out, I've seen some people that will take alkene aromatic ring, and then add MgBr as a reagent. But MgBr doesn't exist. Since it's written this way, I should assume that it's a neutral ionic compound. But Mg is 2 plus and Br is minus. So this doesn't work as a neutral ionic compound. And it's not how we add MgBr. As a good review, we have to have a halide there already. And then we add elemental magnesium. It's not I see this every semester though. It's a common pitfall of thinking I can just slap on the whole group at once. They do have to come in stepwise. How are we feeling on the uses of organometallics? Formation, but one thing that was on here was acyl addition, but that wasn't even one of these. So let's look at some more more of the reactions they do. And Indigo, did you happen to find the question that you were thinking of?
I found one. I think there was two, but the one I found was actually on one of the handouts.
Oh, okay. I'll come over and see it then in a second. Oops. That's not a ring formation. Sorry. Sorry, Andy's like trying to take a picture of it, but I'm not going to let her. I'm going to do this instead. A ring formation by acyl addition rather than by substitution or something.
I couldn't find on the homework where there was one similar, but it's just like attaching that
Mm-hmm.
to the end.
And actually, this was a very long.
I think you went over it a little bit in class, but it was at the very end.
Yep.
If you wouldn't mind touching it up.
Totally. That was a very long synthesis. So I wouldn't give one like that on an exam because it takes too many steps, but I can show you what some of the process was. Yes, 1 point per reagent per intermediate. I will say for the mechanism, I went with 2 points per step. And that's because the mechanisms that I'm having you show, I'm anticipating there only being 3 things for you to show, 3 steps for you to show in the mechanism. And 3 points for a mechanism is not enough. So I doubled it, 6 points for the 3-step mechanism. But remember, what I say is that points are derived from the number of steps or the number of reagents and intermediates. So it doesn't have to be a 1-to-1 ratio, but it's related to. And he's like, he keeps saying it's something about.
Oh, can I ask you a question about like writing out stuff like on the exam? I don't think you don't care like if we draw a benzene with the circle in it. Like,
So long as the
like I can,
electrons are not relevant to the mechanism, no, I don't care.
oh, I just mean like instead of that, you don't care if I just put like the 3 pi bonds.
Oh, not at all, no. I think I told you guys earlier, this is bad.
Yeah, I don't like that.
And that's okay, you don't have to. It's bad because it assumes that there are 6 pi electrons. It assumes there are 3 alternating pi bonds. But that doesn't follow bond line structure by any means. So no, you can absolutely show the alternating double bonds. I do it because I don't even like drawing my hexagons normal. I want to be quicker. In fact, you guys might notice there's a lot of times that I abbreviate after I don't need a ring. I abbreviate it as pH. I do want to point out, when you have a di, tri, poly substituted ring, you can't abbreviate it as pH. Like this, I've had people try to draw this as an intermediate, and they'll draw it like this. Is it ortho, meta, para?
I always see the circle and I always think it's phenyl, because that's how you see phenyl like everywhere.
What's phenyl?
The phenyl.
P-H-E-N-Y-L?
I know, but like that, like how it's always like shown, like benzene, it always has the bonds, but then they always do the phenyl, but with the circle. I don't know if you've noticed that. Like I don't know why, but everything I've like seen, like I don't know why they do that.
You're saying they never show benzene unsubstituted with a circle? They always...
Have the circle thing like that. They always like on a lot of the material, they show phenyl with that, but then benzene always shows the bond.
And when you say phenyl, you know phenyl is just what we call benzene as the substituent.
Yeah, I know.
So when it's connected to something else. Huh, I haven't noticed that.
Yeah, that's something I've noticed.
Interesting. Who wanted ring formations? Do you have the product? Did you try figuring it out?
No,
I didn't show the aqueous workup. This should be 1, 2. Do you want to try or do you want to see me do it?
I want to see you do it.
Yeah?
Yes.
I think that already also has got something wrong.
Which one? Down here?
Yeah, no, the left, the orange one.
Yeah, I didn't really count my carbons. If this attacked this, you're right. My carbons were wrong. I just didn't want to show a four-membered ring forming. But counting your carbons was crucial to doing that, and that's what we should do up here as well. Bad way of showing it. This is going to become my nucleophile. How can I possibly know that? The bromine there reacts with the magnesium, becomes the organometallic carbon. My nucleophile attacks my electrophile. How do I know that's my electrophile? How do I know the carbonyl carbon is my electrophile? Electronegativity of the oxygen pulls electrons towards itself, leaves a partial positive at the O. So 1 attacks 2, connected by 3, 4, 5, 6. Mapping your carbons helps you figure out that the product should have a 6-membered ring. Carbon 1, 2, 3, 4, 5, 6. Anything missing? Where? Carbon 2 had a bond to oxygen. Carbon 2 still has a bond to oxygen, but it's gone through acyl addition, so it's now OH. The magnesium is now a part of the aqueous byproduct waste. The magnesium has been removed. Ring formation. Good example? Yeah. This was a ring formation that formed an alcohol. Could I do a ring formation that makes an alkane? And could I have it be a similar starting material? There's a few options here, to be honest. Yeah, so I could do elimination of the OH to make an alkene and then hydrogenation of the alkene. But I mean using organometallics. Could I do a ring forming reaction? Not by acyl addition, but by SN2, I could form a Grignard at one of 2 halogens and have that Grignard attack the other halogen position to substitute. That is SN2. Since I'm looking at an aromatic ring, I could also do SNAR, NAS. One of the halogens becomes the nucleophile. The other halogen remains electrophilic. Yeah? Formed a ring, but this time it formed an alkane ring because I didn't do acyl addition, so I wasn't left over with any CO bonds. This time, one nucleophile substitutes a leaving group. Done. What do you think? All right, and now to Indigo's question, this was one of the reactions, one of the syntheses on that worksheet from last week Thursday. And starting material does have alkane. It also has benzylic. Because of that phenyl group on the end, the carbon attached to the benzene is benzylic, which gives me slightly different reactivity than just benzene, right? Slightly different reactivity than just alkane. Like, if I want to do radical halogenation, I can do radical halogenation at the benzylic position really easily. And Indigo, your question was, how is it that I add this alkene group to my original alkane chain? And now that I see the problem, I want to point out something else. It's not just adding a carbon-carbon bond, although it's true that it's an alkene carbon bond to your original alkane carbon, but it's actually adding that group, vicinal, to an alcohol. Carbon-carbon bond formation adjacent to the formation of an alcohol. That is a pattern that I want you guys to be familiar with. What intermediate, what reagent will go through a reaction to give a new group and an alcohol on adjacent carbons? Epoxide. The epoxide ring gets attacked at one position and opens the alcohol onto the other. So this can have an epoxide intermediate. And like I said, this reaction I think had like 5 steps. That's too many for a midterm exam. If I want you to be able to finish it in time, I can't have you do that many steps. Mapping my carbons allows me to more easily see what my other reagent needs to be. So let's call this phenyl is 1, benzylic is 2, 3, 4, 5. I need to have a reagent that has 4 and 5 so that 4 can attack carbon 5. Hi, Haley. Carbon-carbon bond formation means that carbons 4 and 5 should be part of a Grignard or organolithium. So here's carbons 4 and 5. Attached to making them an organometallic, attached to a metal. But of course, anytime I want to end with that alcohol, I'll need to convert from nucleophilic conditions and do an aqueous workup afterwards. Oftentimes, where epoxides are useful, acyl addition is also possible. Maybe not always, but often. It might just take longer. It might take more steps. How would I describe this process? By naming the reaction. What kind of name could I give to this? I can form the epoxide by halohydrogen elimination, but during this step, organometallic alcoholation.
Oxidation.
No, it's actually not an oxidation.
I don't know.
But do you remember earlier how I said acyl addition is when we take a nucleophile and we open a carbonyl? Technically, this is opening a carbonyl in both directions. I'm adding a hydrogen to both atoms of the carbonyl, or I add a carbon to the carbon and a hydrogen to the oxygen. But they're both addition because they consume a pi bond. And they're both starting with the acyl group. So acyl addition is not the best name, but it is the name that I use because it's the name your textbooks will all use. Acyl addition is thought of as this nucleophile adding across the carbonyl. Reduction is an addition reaction to the acyl group. But instead of calling it acyl addition, we call it reduction. I don't love this. This is a big term. It's very broad. And we use it for a specific example. That's what I just wanted to point out. Okay. Epoxide ring opening. Ring opening. That's a good name for it. If we wanted to be more specific, ring opening with a Grignard. And that's what I wanted to have over here. Ring formations and ring openings. And actually, as it turned out, with the alkane, that was actually one and the same. We just had to convert the alkane eventually to have other functionality that could go through a reaction with an organometallic. Okay.
Just to be sure, LAH was a strong reducing agent, right?
Yes. And so anywhere that I've used LAH, in all of these cases, I actually could have used NABH4 as well. I just wrote LAH because it was the easiest to write.
But isn't NABH4 the moderate reducing?
And all of these are reactive to the moderate reducing agent. All of these here are. If they're reactive to NABH4, they're also reactive to LAH. Not everything that reacts with LAH reacts with NABH4. I just got lazy. You're right, I should have put NABH4. Since it is more selective, then I know I could have also used LAH. Okay. Okay. Which I'm going to take this down if that's all right with you, Heidi. Okay. I want to talk a little bit more about epoxides. Jackie, this was your concept, right? Epoxides that you were asking about? Right. How do you feel on our organometallics? Do you feel like we've covered it pretty well?
Yeah, better now.
Great. Who had epoxides? Yeah? There's a couple of other instances with epoxides.
How'd you make that one?
How'd I make what?
The epoxide.
How'd I make the epoxide? You want to see the full synthesis again? I would do halogenation here. Do you guys remember this reagent? What's this do, Yoon? Bromination at the benzylic position. It's essentially Br2 in light. And that's actually what the B stands for. You know what that structure looks like? It's pretty fun. It's not every day you get to see an N-Br bond. N-bromosuccinimide. I might be wrong. This might have a...
Instead of NBS, can it be like HBr?
No.
So it has to be NBS.
No.
Is it BR2?
BR2 or NBS, but HBr doesn't do the same stuff. HBr and peroxides will make radicals. these are all three radical reactions. But HBr with peroxide will not give us the same stuff that Br2 in light gives us. Useful for radical halogenation, take off a hydrogen, put on a bromine. Useful for anti-Markovnikov alkenes. Quite different, yeah? HBr consumes the alkene. Br2, NBS, they don't actually consume an alkene. They wouldn't react with it. That's a good distinction. Okay, so NBS or Br2, just to put some functionality here on the benzylic position. And then I would run elimination. If I'm looking to run elimination, a great option is tert butoxide. Since the easiest pathway here is for me to make it an alkene, MCPBA makes the most sense. I could go from the alkene to halohydrin addition, and from halohydrin addition to the epoxide, but that would just add an extra step. So rather than having the halohydrin. However, if at any point you could add halohydrin. Oh, I think I'm off the screen. What reagent does my halohydrin need to form the epoxide? NaH. Or some other strong base with a lot of heat. Need to deprotonate the oxygen so that the oxygen can act as a nucleophile and substitute the bromine. Back to epoxides. I always forget to say this. I probably won't give you guys like a break today. So if you need that break, take it. Get up, move around, get your blood flowing. But typically we have just enough time to get through everything. So I'm going to keep going. With epoxides, in this reaction, am I doing an epoxide in acidic conditions or basic nucleophilic conditions? Nucleophilic. That's evidence because I have an acid workup. So I must not be in acidic conditions if I have to add acid afterwards. Let's stay on that boat and let's look at some other basic nucleophilic conditions. And why don't we keep with the same epoxide? If I introduced here a strong base like methoxide, I should expect substitution at the least substituted carbon. My nucleophile attacks least substituted. My alkoxide forms at the more substituted position. And then, of course, we follow that up with an aqueous workup. So what if I did this? What if I ran my epoxide with hydroxide and then followed it up with an aqueous workup? An alcohol on the least substituted, and what about on the most substituted? Huh? I heard something. Oh, and the nucleophile attacks at the least substituted. And on the most substituted. Oh, that's just a vicinal diol. Cool. It would give the exact same thing if I did the hydration in acidic conditions as well. Hydration of an epoxide, adding water across an epoxide, just gives a vicinal diol. Doesn't matter if it's from acidic conditions or basic conditions. Vicinal diol.
So if this was to run in an acidic condition, what would it look like as a reaction?
Well, the intermediate will protonate the epoxide first. You get a protonated epoxide. That pulls on the bond to the more substituted carbon to help stabilize that charge a little bit better, and then your nucleophile attacks.
But on the arrow, would it like show like?
Oh, well, we wouldn't need 1 and 2. We would just say H2O, H3O plus.
I see.
Okay, so can someone put into words for me, please? When I did this with an alkoxide and made an ether, why did I stay with O minus? And then when I did it with hydroxide, why did I get an OH? Aqueous workup. The main difference is the aqueous workup. How many of you had that on your unit test? Yeah? The problem that said no aqueous workup to specifically keep an ether, an alkoxide to keep running reactivity with it. So you can essentially do a Williamson ether synthesis. You can take this epoxide, take this alkoxide and use it as a nucleophile. By the way, did you guys know that all unit test questions are now available on the midterm module? There's a new test on the midterm module that has every question from all of the unit tests. It's not graded. It's like a. It's a.
Midterm examiner? No. Which one? This is what the module.
It should say all unit test questions.
This is what the module. Which one?
It says all unit test questions. I want you to find it. Okay. I just wanted to make sure I wasn't hallucinating. All unit test questions. That way you can see all the questions you got through all the unit tests and all the questions you didn't get across all the unit tests. And it will give you the answers when you submit for the multiple choice, but of course there's no answers for the short answer. So it gives you more practice problems on the short answer, but if you have questions on those, you just send them over to me. Okay. In epoxides, we can also look at acidic conditions. And generally here, we're going to consider alcohols and water. I always introduce the nitrile, the cyano, and then I never end up incorporating it in the midterm. It just escapes me. But we will work with the nitrile more in the second half of the semester. So here I get to control the regiochemistry of where my ether forms. But like Haley brought up, if I did this with acidic addition for water, it's just a vicinal diol. Nothing really changes there. Okay. Peyton, I want to go back to some of the reaction names. Are there any names that you can think of that you want to hear? Or do you want me to just write the name? Oh, and acylation.
The Williamson ether, which you just talked about.
Oh, good. So how do you feel about acylation and alkylation?
Alkylation just means like an alkene.
Not an
Or
alkene.
alkane.
Yeah, alkyl.
Alkyl group, so alkene or alkane.
Yeah, I guess actually more alkane.
With like a halogen connected to it?
No, not always. Just alkyl. Just sp3 carbon.
Oh, okay.
To make it, yes, a halogen will be attached.
Oh, okay.
Sometimes. A lot of times we'll refer to this alkylation in the context of acetylide ions. We looked at this in OChem 1. We can alkylate the alkyne. And that needs to be an sp3 hybridized carbon to go through SN2. But then we learned how to alkylate on the aromatic ring. And this also needs to be an sp3 hybridized carbon. But it actually uses a carbocation intermediate. So as long as we can form a carbocation intermediate, hey, I know how to form carbocation intermediates from OChem 1. Alkenes in the presence of acid form carbocations. I can alkylate that way. I've added an alkyl group. I've added an sp3 hybridized carbon. And I think I'm not doing a good job of explaining this in class. I get some creative answers for alkylation in multi-step synthesis problems. I want to add an alkyl group to my, an alkene group to my ring. So I'll add the group I want with an halogen and my catalyst, and I should get it, right? Right, but it doesn't work. It's because the intermediate that I need, or the intermediate that I will get, is this carbocation, which is very hard to form. We do form this carbocation when we protonate an alkyne, but I have not seen a textbook or any other resource online that shows an alkyne precursor to this group. As soon as I see it, I might start teaching it. Maybe we should go in lab and try to do it, but I'm not sure that it works. And it's because this certainly doesn't work. So I do want to talk about this. What if I wanted to make this group? What could I do? You guys okay with the epoxides if I erase it? Any suggestions on how to make styrene? Brominate the ring. All right, let's start with bromobenzene. Now what? Yeah, Camille? Oh, Ozzy, sorry. Right in the perfect line. A what? Like this. This is Friedel-Crafts alkylation. But it doesn't work. And it also now it wouldn't give me styrene, it would give me bromostyrene. You know what? I'm not sure that alcohols do well in these aromatic rings as nucleophile reactions. I've not seen it, and I think that it's not a desirable reagent. To get rid of the alcohol?
Oh, I'm meaning from the bromine to get to the terminal alkyne.
There's no carbons to eliminate to make an alkene.
Is this kind of like the homework assignment that we had to do? We had to make. I just did this. We actually had to make it and then break it. I don't know if you get what I'm saying.
Yes, but no, I don't think you'll need to do that.
Oh, okay.
There is a reaction here that would work great.
I was thinking maybe we could try freedom crafts with fluoroethane and then we like substitute.
Right, longer, yeah. I could put an ethyl group on just by Friedel-Crafts alkylation, and then I could radical halogenate the benzylic position, and then I could use tert butoxide to eliminate and make the alkene. I like this idea though with bromobenzene. Can I get right from here to here? What a terrible ring. Organometallics. NAS. Aryl halogen is replaced by a group. That group I need to be the nucleophile is not an oxygen group, not a nitrogen group, but a carbon group. And here's what I want that carbon group to look like. It's flipped. Instead of having the alkene carbon try to be the electrophile, I've made the alkene carbon the nucleophile. And I attack the aromatic ring. Now it's on. Well, I don't just attack the aromatic ring. I attack the aryl halide position so I can substitute the aryl halide. All right.
Could you let me why you're doing the acid workup after that?
I'm force of habit. I don't actually need the acid workup. You're right.
Could you use Mg instead of Li? Like, it have to be
Always. Anywhere that you see Li, you can swap with a magnesium halide. Yep. Those are interchangeable. In fact, sometimes I look at organolithiums and I call them Grignards because to me, they are the same reagent. The only difference is preparation. Do you want to work with lithium or do you want to work with magnesium? But they do the same thing. And Grignard is meaningless. Grignard doesn't mean magnesium, you know? It means some guy that lived a long time ago.
So you don't need an electron withdrawing group to run an NIS on a ring?
Correct.
Okay.
But you do need a leaving group.
Yeah, I thought you needed it. Okay.
An electron withdrawing group will make it easier. It will make it happen faster. But if you remember in lab, you guys were taking this reagent and turning it into this reagent. But of course, that happens over time, which means that as this forms, if there's an excess of this, they react together. NAS, without an electron withdrawing group. In fact, you can even have weak electron donating groups, like a methyl group, or any alkyl group. But what happens as soon as you start putting these guys on? Now the activation barrier skyrockets, and it's unlikely that it will do NAS. So electron donating groups prohibit the reaction, but electron withdrawing groups just activate it better, lower the activation barrier. Okay. Alkylation versus acylation. That was alkylation here versus acylation. And I do want to bring up a couple of points on acylation. we have primarily looked at the acid halide being our acyl group, but we did notice that the acid anhydride can be the acyl group. This is just a little bit more complicated since it adds a second carbonyl. But a lot like the alkene in acid alkylation, this acylation doesn't require a catalyst. I have noticed a lot of people that will try to flip this, and they'll try to run NAS instead of EAS to do acylation. And they'll add an acyl group that they are trying to make nucleophilic. I like the thought, but the carbonyl carbons behave quite differently from alkene, alkane aromatic rings. Those carbonyl carbons won't form organometallic carbons. So much like how this alkylation of an alkene does not work, this acylation by acyl organometallic doesn't exist, won't work. All right. I want to say that's pretty much all of the names that you probably came across, other than oxidation reduction. So let's talk about resonance forms and EAS, NAS mechanisms. Who can help me write out the 3 rules for resonance forms? Who can give me the first one? Let's pass this across 3 different people. Do you know the number? Appropriate charge placement is not our first rule. Maximized octet is not our first rule. Minimized charge. What did you say? Those are rules for aromaticity. Number 1 is minimum charge.
Oh, I thought somebody said that.
Somebody did say that.
Oh, okay. I was like, wait, what?
Oh, but Peyton said fully conjugated,
Yeah.
which is rules for aromaticity, not resonance.
Oh, sorry, different world. I can't hear very well.
First, we minimize charge. That's the maximum resonance. That's the major resonance form. Then, when all charges have been minimized, what do we look for? Maximized octets. Then, after octets have been maximized, what do we look for? Charge placement. All right, where would be the best place? Oh, I should just have an aromatic ring. What am I doing? It's going to make the most sense on an aromatic ring. Where would be the best place to put a positive charge in this structure? I'm hearing between oxygen and nitrogen.
I'm gonna say oxygen.
Tertiary carbon. And this is going to be an intermediate for an aromatic ring during an EAS reaction. When you put a positive charge on carbon, you're following appropriate charge placement before following octets. When nitrogen and oxygen have that positive charge, they still have an octet. But when carbon has the positive charge, it minimizes an octet. It doesn't have an octet. So that's less valid than the forms that have less appropriate charge placement but have maximum octets. So now between oxygen and nitrogen, where both octets are met, where's the appropriate charge placement? On the oxygen. Sorry, on the nitrogen.
He's like hearing me, he's like, I'm it.
I really just let something in my ear and out my mouth.
Is it more electronegative takes the negative charge? Like it would
Yes.
refer to?
More electronegative prefers negative charge. Less electronegative prefers positive. Which is why carbon should prefer the positive, but when it does, it breaks the octet.
Okay, in this situation, is that because, like, I'm thinking about one of my unit testings, is it because it has the H on it? Because on one of my unit tests, it had a double bond with an oxygen, and it took the positive charge when it had a BR attached to it.
I think you're talking about the nitro group, which, when expanded, always has a positive charge. It can't not have a positive charge. But when the nitro group acts as an electron withdrawer, and it takes a pi bond out of the ring, it still has a positive charge on the nitrogen, but now both oxygens have a negative charge. But if I give you NO2 and then I show you this form, it's easy to think I've maximized charge. It's easy to think I've gone from 0 charge to 3 charge. I was just hiding the 2 charges. I was just not showing that they were there, that they cancel each other out. So I haven't actually increased charge, and I haven't created a charge on N. But actually what I've done is place the negative on O. Is that what I think that's what maybe you're referencing. And that's my next point. Notice that in this problem, what I showed was incorrect. God, I'm good at this. I gave you a nucleophile attached there. I should have had an electrophile attached there. The ring has lost electron density and given it to the electrophile. Now let's flip this. And we'll keep our nitro group. We'll keep our, let's keep a carbonyl group. Sulfonyl or nitrile, those are your other options. Sulfonyl, SO3H.
I don't know. Would it really be that happy being ortho?
Now I don't want an E, I want nucleophile. Goodness gracious. Where's the best place to put the negative charge in this structure? You're funny.
Well, I mean, if it's moving.
Listen, I'm sorry. I took it personally and I shouldn't have. You said funny.
No, I said fun.
Play it back.
That's fun.
He's like, oh really? I haven't recorded.
Where's the best place to put the negative charge?
So you're asking for the major. That's pretty
Yeah.
much what you're asking. Okay.
Why?
I think that's just more electronegative. Or we can expand its octet, right?
Yeah, the sulfur has expanded its octet already. Are you saying you want to put it on the oxygen in the sulfonyl or on the sulfur of the sulfonyl?
I was thinking that you could push that double bond between S and O to give O and negative charge.
Yes. So put the negative on the O in sulfonyl. Why not the O on nitro? Why not the O on the carbonyl?
Isn't it more electron, like, it holds it?
Oxygen is more electronegative than oxygen?
They have more oxygens.
Yeah, but I can only show it on one at a time. I would say here they're all equal. I mean, they're not. There are distinct differences, and I think largely it comes down to the sulfur, nitrogen, and carbon. And that's not something you're going to be tested on Thursday. By the way, did you know there's a review session tomorrow night? Wednesday at 5:30 upstairs.
Don't they record it?
I don't think they'll be recording it. I think they are going through the practice midterm that's on Canvas. All right, so there's several here. Let's show the negative charge on the sulfonyl. But then we could also show the negative charge on the nitro. Oh man, this is so long. But then we could also show the negative charge It's hard to say where the negative charge is most appropriate. Should it go on O, or should it go on O, or should it go on O? Those would all be major resonance forms. So let's say that you were showing the NAS mechanism for this. Oh man, and I drew a hydrogen in each of those places, and it should be a halogen. Let's name all the ways I can screw up. I'm even going to abbreviate that. If I wanted to show the electron arrow pushing mechanism for this NAS reaction, God, I'm trying to put boxes to make it look like you can tell what's going on. Right. Nucleophile attacks where the with the chlorine, the aryl halide carbon.
And it doesn't kick it off yet, it works through.
Correct. It breaks aromaticity, forms a sigma complex intermediate.
So the double bond will move up into the first one. Well, either side, but technically I work quad.
Well, I already decided which ones we're going to show in which order.
Oh, sorry.
So we're going to take it from here to the sulfonyl group. So the carbon-carbon bond in the ring needs to break. And it needs to break to the sulfur to make that double bond. Notice that the other double bonds remain unchanged. Then I need to break the sulfur-oxygen bond. There's my first step, nucleophilic attack. By the way, how many steps in NAS mechanisms? One step would be like SN2, something attacks while something leaves, one step.
It happens all at once, I thought.
These all exist at once, but the fact that these exist after this and not the product means that there's at least two steps. Addition, elimination. NAS is always two steps, but with a varying number of resonance forms that you might want to show. So in this case, I would call this a four-step mechanism. Addition, resonance, resonance, and then we'll need to show elimination. I would give you 4 points Or if I doubled it, 2 points for each step, 8 points for this mechanism. Does that make sense? 2 points to show me addition. 2 points between each resonance form. 2 points for elimination. It's a 2-step mechanism, but the number of resonance forms changes the number of steps you have to show.
Quick question, is the reason why you call that a sigma complex is because the pi aromaticity is broken?
Yeah. I don't call it sigma because I came up with it. I call it sigma complex because the textbooks call it that. I'm not sure why they call it sigma. How do I get from here to here? I need to show arrows.
So you have to then break it back like down into the ring.
Reform OS double bond.
And then that double bond on the sulfur. Sorry, my neurological stuff's kind of kicking up, so I'm struggling talking a little, so sorry if I stutter. And then kick that, yep, and then you move that double bond into that carbon, and then that needs to move up into the oxygen, and you need to put in the charge on that. Thank you.
Oh, but that's actually not the structure that I showed next. So that would be valid. But since that's not the resonance form I gave, let's show how to form this form. We'd keep pushing this around the ring, push it out to the nitrogen group. OS double bond reforms. Carbon sulfur double bond moves back into the ring. Carbon double bond in the ring moves over. Carbon double bond in the ring moves to carbon nitrogen. Nitrogen oxygen double bond breaks. That gives me my nitro group holding the negative charge. It would have been super valid to go down to the carbonyl and give this form, but since that's not how I drew it out, I'm going to draw it to this. All resonance forms are related to all other resonance forms at the same time. So there is no correct order to go through. And then from here to the top, ON double bond reforms. CN double bond goes back into the ring. Carbon-carbon double bond comes out of the ring, and carbon-oxygen double bond breaks onto O. This is a very long-winded game of spot the difference. What bonds need to reform, what bonds need to break. Electrons can only move one atom at a time. They can't be lobbed all the way across the structure. They can only leapfrog atom to atom. Elliot and then Ozzy.
We're missing hydrogens on the hydroxyl just because we did bromine.
Yep, just because I can assume that hydrogen, bond line structure. Ozzy?
What I was going to say, so we decided, like, because we have the three major, because they're all, like, they all pull the electrons, right? Okay, I just wanted to make sure.
Yes, yes. All right, now how do I get from this resonance form to my final product? How do I show the elimination step?
You gotta put the double bond.
Oxygen-carbon double bond reforms.
You gotta rebond it, and then it kicks off the group it hates, because it hates. I don't know.
Carbon-carbon bond moves back into the ring, moves my other carbon-carbon bond over, kicks off the halogen. I've reformed aromaticity, but now I have a nucleophile attached instead of my halogen. Let's do something similar with EAS. How many steps is an EAS mechanism? Minimum 3. Activation of the electrophile. If it's chlorination or bromination, that's 1 step, and then the ring attacks the electrophile. And you have to show that. I'm assigning points for that. So if you don't show activation of the electrophile, then you've lost some points. If it's acylation or alkylation, that has an additional step associated, which is formation of the carbocation. So activation of the electrophile is at least 1 step. Then you have the resonance forms. That can vary. And then you have elimination. So activation of the electrophile, ring attacks the electrophile. There could be resonance forms there. And then elimination. that's a deprotonation. Here we kicked off a group, but with EAS, hydrogen is deprotonated and electrons go back into the ring. So at least 3 steps. That could be 3 points, that could be 6 points if I'm deciding to double it. So let's go with this one that I had here. Let's just say we already have our electrophile. I'm going to skip that for now. And I want to show the formation of my first major resonance form. I want to show it right away because, to be honest, nitrogen is the reason the carbon is attacking from where it does. So I'm going to show that form first.
Sorry, I could color with my shades. What is that? Where are your groups? Sorry.
Nitrogen top left, oxygen ortho or meta to the right, and a methyl meta down.
Okay.
Since nitrogen is our strongest activator, its lone pair forms a carbon-nitrogen bond. Breaks the octet at this carbon. So this carbon needs to lose electrons, and the ortho carbon uses electrons, attacks my electrophile. Yeah, I should use a different color, huh? I've just formed my major resonance form. Now, I think we could argue that the carbocation on the tertiary position is also major, but it's not as major as when the oxygen and the nitrogen hold it. I'm not going to leave this ambiguous on the exam. It will be obvious how many major resonance forms to draw. But I want to show you how to get over to this other resonance form. I'm going to ignore the one where the tertiary carbon holds it. But I do want to say, if I need to get over to the resonance form where oxygen holds the positive charge, that means oxygen needs to start donating its electrons. So I'm going to start my arrows from oxygen. Oxygen donates electrons, breaks the octet. This carbon needs to lose them. Pi bond shifts over, pi bond shifts over, and the CN double bond breaks back to the N. I should never show a positive charge moving. I should never have an arrow that starts at a positive charge, because positive charge is the lack of electron density. My positive charge moves as the result of my electrons moving.
When that happens and when that resonance forms, wouldn't it like kind of try to kick out that hydrogen and like make it just like oxygen since oxygen's better?
No, it doesn't try to, because these don't exist. This isn't forming. This is always there. These are silly little impressionist paintings, like we're kindergartners painting landscapes. And it's beautiful. Like when you run home to mom and show her your pictures. Good job. You tried so hard to represent reality. And you did all right.
Oh, now you're really making me feel better when you mark me off. Oh my
No, I'm talking about us as humans, not you as my students. Us as people trying to understand chemistry. We are the little kindergartners.
Missed a sunbeam.
Yeah, exactly.
That grass isn't even pointy.
All right. Now, I do understand what you're saying. Why doesn't this oxygen want to take its electrons back and get rid of the H? That's actually not the most acidic hydrogen. Usually it is. Oxygen holding a hydrogen is typically the most acidic. More acidic than nitrogen because it's more electronegative. More acidic than carbon because it's more electronegative.
But it's the hydrogen that donates, right? Isn't that more?
No, the hydrogen doesn't donate. It's the oxygen.
No, I meant like the one that's more acidic.
But in this case, the most acidic hydrogen is actually on the carbon. So the hydrogen most likely to be deprotonated is on the carbon. because then I can reform aromaticity. And aromaticity here is way better than having a deprotonated carbonyl, right? So actually comparing the acidities, carbon way outweighs oxygen in this structure. Good question, though. I think I've run out of time. I do want to say one last thing. Earlier, some of you pointed out that a primary carbocation, secondary carbocation versus tertiary carbocation, more substituted, more stable. I don't know that we ever hit on this, but how would you rank the stability of these anions? Totally, the charge flipped, so the stability should flip. A positive charge is more stable when it's surrounded by more electron density. It's like clouded. It's hard to tell there's a positive charge there. But a negative charge would push back against all that electron density. So a negative charge is more stable the less it has to push back against. And then positive charges, they increase with substitution, and then they start over with resonance. Having any amount of resonance is better regardless of the substitution, and then it increases with substitution. So alkane carbocations, and then allylic, and then benzylic, all in increasing substitution within themselves. Yoon?
I do have a question with acylation of the EAS. There's another agent for the acid anhydride. Do we need to know the mechanism of that one?
Not the mechanism. You do not need to know the mechanism for the acid anhydride, just the acid halide mechanism. And there's a 50-50 chance it shows up. Or actually a 1 in 4 chance it shows up. Because I'll give you one EAS. Could be bromination, chlorination, alkylation, acylation. I'll give you one NAS. It could be a Grignard, alkoxide, or a nitride. Amide. Okay. Wednesday, 5:30, SI 101, review session for you guys held by Johnny Pope. Hope you can make it. I'll see you all Thursday. Where? Here. What time? 5 o'clock. Our class is at 5. I will not start until about 5:10 or 5:15 to give you guys a chance to come in, but you should be here around 5 in case we need to get started early. See you Thursday.